Alright, so here is an example of a more complicated system of equations. X plus 3y plus 2z is 2, 2x plus 7y plus 7z is negative 1, 2x plus 5y plus 2z is equal to 7. Now, in the previous video, when we had two variables, we're able to graph the equations as lines in a plane. And these three equations can be thought of as uh, planes within three-dimensional space. And if we up the number of variables, we can think of them being the corresponding structure in a higher dimensional space. But at that point, it becomes very difficult to use sort of geometric intuition to understand what's going on here, much less to actually find the point where three planes intersect. So we're going to begin by approaching this algebraically. Now, the first thing I'm going to do here is I'm going to convert the system of equations into what's called an augmented matrix. So when we have an augmented matrix, what's happening is we're taking the essential equation of these linear equations. So each column represents a variable. So the x variable in the first column, and then the y variable, the z variable, and then the constants in its own column. And then each row represents one of the equations. So we have x plus 3y plus 2z is 2, 2x plus 7y plus 7z is negative 1, 2x plus 5y plus 2z is 7. And so we've captured all of the essential information we need to know in this matrix here. And so what we're going to do now is we're going to manipulate this matrix algebraically in order to give us a new system of equation from which it'll be much easier to deduce what the solutions are. So let's talk about what are some allowable manipulations that we could do. So the first thing we're allowed to do is we're allowed to swap rows. And this is just a way of saying, look, I have these three equations. It doesn't really matter which order I write them in. They all have to be satisfied. So if I took these two rows and I swapped them, does it really make any difference? Probably not, right? So that's our first allowable move. The second allowable move is to multiply a row by a constant, non-zero constant. Equivalently, that means we can multiply by a fraction and divide. So what's the point of this? Well, we've seen this all the time, like in algebra before, right? If you have 2x is equal to 6, then you divide both sides by 2 and you get x equal to 3. And all this is saying is we can still do things like that here. And the third thing we're allowed to do is add multiples of rows to each other. Now, why this is allowed is a little bit more subtle. But if I take a look at this and that, and then I take a look at this and that, and I say, all right, if this and this are the same, and this are the same, if I add it together, wouldn't the left-hand sides and right-hand sides still be the same? If I doubled this and added it to that, wouldn't that equality still hold? And so what we're doing then is just creating a new equation out of the ones we already have, and the system as a whole preserves the same solutions. So armed with all of this, let's go ahead, take our systems of equations represented by this matrix here, and simplify it in such a way so that we get a cleaner system of equations. So the first thing I'm going to do is take -2 times the first row and add that to the second row so that I get a 0 in the first entry. So I get 1, 3, 2, 2, and -2 times the first row plus the second row gives me 0. -2 times 3 is 6. -6 plus 7 is 1. -2 times 2 is -4. Plus 7 is 3. -2 times 2 is -2. Plus -1, or -4. Plus -1 is -5. And I didn't do anything to the second row. Now I want to do the same thing to the third row. So -2 times the first row plus the third row into the third row gives me 1, 3, 2, 2, 0, 1, 3, -5, and then 0, -1, -2, 3. Alright, so -2 times the first row, added it to third row. Good. Now I want to take the second row and add it to the third row and store that into the third row. So first row stays the same, second row stays the same. And then the first row added to the third row gives me 0, 0, 1, -2. Then I'm going to work backwards. I'm going to take -3 times the third row and add it to the second row. So that gives me 0, 1, 0. -3 times -2 is positive 6 plus -5 is 1. I'm going to take -2 times the third row and add it to the first row. And that would give me 0, 1, 0, 1, 0, 0, 1, -2. And in my top row, I'm going to get 1, 3, 0. -2 times -2 is positive 4 plus 2 is 6. And in my last step, I'm going to take -3 times the third row, or second row, and add to the first row, store it in the first row, and that's going to give me 0, 1, 0, 1, 0, 0, 1, -2, and 1, 0, 0, 3. Okay, well that was a lot, right? But we can see that this system of equations is much simpler than the original one we started with. If I go through and look at this, I can now rewrite this as a system that says, well, x plus 0y plus 0z is 3. 0x plus y plus 0z is 1. 0x plus 0y plus z is -2. In other words, x is 3, y is 1, z equals negative 2, right? We basically got all of our solutions right there. So to verify, if I say, all right, what did I say? X is 3, y is 1, z is negative 2. Let me make sure that that's in fact what, yep, we got. All right, then we could check. 3 plus 3 is 6, minus 4 is 2. 6 plus 7 is 13, minus 14 is negative 1. 6 plus 5 is 11, minus 4 is 7. So yes, all three things are satisfied. And so what we have found here then is the solution to our original system of equations. Now, there's probably a couple of things going on through your head right now. One is that this step to find a system of equations is extremely complicated, and it takes a lot of computation, and there's a lot of places to make little mistakes, right, with sign errors or getting division wrong. And the worst part is that this problem that we used for this example was actually designed to have a nice computation. If you look in our text, I've written out an example that's not nearly so nice, with far more steps and fractions and division by fractions and so on. This is a pretty gnarly way to go about finding the system of equations. But it is the standard sort of ubiquitous method for finding these things, particularly with higher variables. So this whole process is called Gauss-Jordan elimination. And the resulting matrix that we found is what's called reduced row echelon form, which means we have ones in the diagonals, we have zeros above and below those ones. Now, having watched me do this, you're probably not relishing the prospect of doing it yourself. That's okay. In the next video, I'm going to show you how we can use technology to do the Gauss-Jordan for us and produce reduced row echelon form matrices much more readily. Alright, see you in the next video.